Okay, so let's begin. Today we will, and in the next lecture, we will discuss Darroch's equation for electrons. And we will also solve Darroch's equation and approximately and find corrections for a potential like that of hydrogen atom, like a central potential. And we'll see that relativistic effects like spin and Darwin term and other relativistic correction to energy, they naturally come out of Darroch's equation. Well, there might be a couple of things that you might not be able to maybe fully grasp, but I'll try to make at least point you to a way that okay how you can find that, but hopefully most of it will be digestible at your level. Okay, so we know that Schrodinger equation came in like 1926, somewhere around that. And as soon as it came and people saw that it's successful in explaining a lot of quantum phenomena, but people also realized, including Schrodinger himself, that that equation is not applicable to relativistic particle, special relativistic particle, that it cannot take into account the special relativistic effect. And many people actually started to work on generalization of Schrodinger equation for relativistic particles, including Schrodinger himself. But most notable initially were Klein and Gordon. So there's a Klein-Gordon equation, which is sort of initial attempt at studying the relativistic particles using Schrodinger equation. And the other thing that people knew at that time that was not being taken into account by Schrodinger equation, but that has already known at that time, and that was that the impact of electron spin. And because the spectrum showed that electron does have some property which is proportional to angular momentum, which is giving rise to some magnetic dipole moment of electron, because when the atoms were put in an external magnetic field, it was changing the spectrum. So people knew that there is something more with the electron that's going on. And by assuming the electron to have spin, they were able to explain the spectral, branching of lines. But it wasn't, it also has to be explained by some fundamental theory. So initial attempt by Klein and Gordon, they were not able to correctly predict the impact of spin. And then Darroch came along and he came up with an idea of quantizing sort of wave function and states in such a way that spin automatically and naturally, is taken into account. So let's start with Klein-Gordon equation, and then we'll go to Darroch's equation. So Klein-Gordon, they actually started in the same way as Schrodinger started. That Schrodinger equation was sort of the quantization of this equation. So if you think about Schrodinger equation, you can think about like this. So we have kinetic energy plus potential energy. So you quantize it. So this E was E square over 2m classically. So this is Newtonian kinetic energy plus, some potential V of R. So in general, this could be anything. So you quantize it like this. So this E is converted to this partial T, and this psi is a wave function now that tells the state of the particle. This P square goes to iota h bar del square. So this becomes minus h bar square 2m del square psi plus V of R psi. So this was Schrodinger equation. This is essentially the quantization of classical energy equation. Okay, so total energy is kinetic plus potential, and by identifying this P, operator with iota h cut del, and identifying this energy operator with iota h bar partial t, you can get Schrodinger equation. So initial attempt naturally was quantizing this relativistic equation, that E square is equal to m square c4 plus p square c square. So this is the total energy equation that we get from Einstein's special theory of relativity. So the initial attempt that people also attempted was this, that you know, change this E to iota h bar partial t, and then this p2 minus iota h bar del, and you get a relativistic quantum mechanical equation. But this was not that, you know, successful, and you operate it, you know, on some operator, let's say psi. And then the insight that actually came from Dirac that, you know, helped then start the establishment what was later called quantum field theory, that was able to explain the impact of spin, etc. So Dirac's major contribution, in my view, was this realization that when you have a particle with properties like spin, etc., you can't have a scalar psi represent the state of the particle. So he postulated that spin, let's imagine that spin is coming from some internal structure of the particle. So it means particle internally also has some state. So a single scalar variable psi cannot represent the particle fully, because, you know, particle have external position, etc., and then it also have internal structure. So his basic idea was that instead of psi being a scalar, let's assume that the state of a particle is given by not one, but in general, let's say n wave functions. That was a major contribution, I think. And then, you know, after making some more argument, you can start constructing the equation, etc. So this was his basic idea. We'll see that later on, that, for example, for a spin half particle like electron, you should have at least this vector should be 4 by 1, and should be equal to 4, 2 numbers for electron and 2 numbers for its antiparticle positron, and so on. So similarly for other particles. So it means that if you have a spin 0 particle, that might be, you know, represented by an equation like this, or also that the individual components of this wave vector, this wave function vector, they should satisfy this Klein-Gordon equation. But overall, we should have should have an equation that is satisfy this vector psi instead of this, you know, scalar psi. That was, I think, the most critical insight from Dirac that enabled the inclusion of spin and everything, and a more general theory than Schrodinger equation. And let's see how. So once he has this assumption that instead of a single variable, instead of a scalar psi, we should have a vector psi for each particle. Then after this, the next part is that, okay, what should be the form of the equation? And his, you know, assumption was that we should have an equation similar in form to Schrodinger equation. So we have, you know, like this. And just to, you know, emphasize, in most books, you'll see that since Dirac's equation, it's written in tensor form or in component form. So, but I will be using a notation of vectors and matrices simply because I think it's very helpful to imagine and work with initially. Okay, so now our state psi is a vector, which means our Hamiltonian operator should be a matrix now. So this is an n by 1 vector, so this should be an n by n matrix. So this is the form of the equation that he assumed. Now, and this is still unknown, okay? And his first assumption about this Hamiltonian for the particle was that since in special relativity, I'm sure most of you have seen it. If you remember, the spatial coordinates x1, x2, x3, and this time coordinate, some people write with plus or minus CT, they are on equal footing. Okay, so this time is on the same footing as x. Similarly, whenever you see any relativistic equations, the derivatives, if there is, this partial, so these space derivative and time derivative, they also come with the same order and same thing. So if in equation there is, some term with partial t square, then there will be term with partial x square and so on. If there are terms like partial t and other terms are adding, they're also of, linear in partial x and so on. Simply because, this is essentially one interval now. So because of this thing, he said that this h, instead of like this square terms, like this initial attempt, in contrast to this, his assumption was this Hamiltonian operator should be linear in the momentum operator, because momentum operator is nothing but partial x, partial, x1, x2, x3. So this should be linear in momentum operator P, and plus, and this is some, a constant. This is a tensor of 3 rank, but I'm writing it with this weird notation that I have invented, to explain it to you, and I'll say what it is. Whatever that, this is some something that when you multiply with this vector, you get a matrix. And then another term, which is proportional to this, rest mass energy BC square, MC square. So that was, his assumption that we have a Hamiltonian which is linear in momentum, and also have some proportionality to this MC square term. So this is rest mass energy. So this and this, they are yet unknown, but some constant matrices. अच्छा, इसमें जो P है, if you imagine this like this, this is unit vector, let's say along x-axis. This is unit vector along y-axis. This is unit vector along z-axis, or you can also imagine like this. x2 partial x3 u3. So this is P3 momentum है, ठीक है, क्योंकि टाइम इस तरफ है. So this is the usual momentum. अब ये जो अल्फा मैंने ये टेंसर लिखा है ना, this is essentially this. So there is some matrix alpha 1 with unit vector u1. There is some matrix alpha 2 with unit vector u2. There is some matrix alpha 3 u3, so that this dot p is just alpha 1 so this is proportional to that. Okay, so there is iota h bar minus. Anyway, so p1 plus alpha 2 p2 alpha 3 p3. So ये जो alpha ये 3 bars के साथ है, this is just a contracted notation. for a vector which has each of its component as a matrix. जी टाइम इधर है ना लेफ्ट साइड. So आप उधर ले जाए तो then you can easily include that as well. ठीक है जी. सॉरी हाँ आप उस फॉर्म में लिखना चाहें तो लिख लें. There wouldn't be any advantage. मतलब इस फॉर्म के अंदर ये जो P है ये 3 मोमेंटम है. अगर आप 4 मोमेंटम की फॉर्म तो इसको उधर ले जाएं तो उधर है पार्शियल पार्शियल T भी इसके अंदर शामिल हो सकता. ठीक है इसको मैं लिख सकता ना कोई आइडेंटिटी डॉट पार्शियल बाय पार्शियल टी इसमें ऐड कर दें इस टर्म के अंदर तो ये एग्जैक्टली वही फॉर्म बन जाएगी. फिर चौथा आपका वो टाइम वाला हो जाएगा. बट इट्स लिटिल बिट इजियर टू इमेजिन इट दिस वे. दिस इज स्टिल दिस हैमिल्टोनियन इज नो एन एनर्जी ऑपरेटर. ठीक है दिस इज इक्वल टू एनर्जी. सो इस फॉर्म में जो इसकी फिजिकल सिग्निफिकेंस है दैट इज इजियर. ओके एंड देन दिस आल्सो corresponds to your usual interpretation of Hamiltonian operator as well. Okay. So this is just a starting ansat. So this is the assumption that, okay, let's start by assuming that the particle satisfies a wave equation of this type. ये लिखें कि ये एक वेक्टर है जिसका हर कंपोनेंट मैट्रिक्स है. वेक्टर 3 कंपोनेंट वाला वेक्टर है उसका हर जो कंपोनेंट है इट्स अ मैट्रिक्स. Okay, and you have actually encountered these types of things before, but maybe not in this notation. For example, you might have encountered this spin operator. Let's say Sx. Right? So इसमें ये जो each spin operator है, usually it's a 2 by 2 matrix. So you have already encountered, but I'm just explicitly saying what everything is. So the other way is that this is a vector operator to think of it. So this is an operator along x-axis. ये जो alpha 1 है, ये operator उसका y component है, ये z component and so on. और ये भी हम by the way हमने अभी find करना है. So जो known चीज है वो सिर्फ p है इसके अंदर. अच्छा ये c कांस्टेंट वो स्पीड ऑफ लाइट है. सो चूंकि ऑलरेडी हमें पता है कि इसको सॉल्व करके क्या रिजल्ट आएगा तो फॉर कन्वीनियंस ये भी कांस्टेंट है अभी अननोन बट वी हैव रिटन अनदर कांस्टेंट हियर. ओके सो दिस इज द स्टार्टिंग इक्वेशन. बीटा वो कोई मैट्रिक्स है यानी कोई कांस्टेंट मैट्रिक्स है. Okay, so Dirac assumed 2 things. Number 1, that the wave function is now a vector. And number 2, that Hamiltonian has this form. That's all. So let's now, by the way, I just want to give one comment, and that is that even in the Schrodinger equation, and in the Klein-Gordon equation, if there is external electric or and magnetic field, then your equation changes like this, that your energy goes to energy plus this phi is electric potential, and your momentum operator then becomes minus iota h bar del plus p, बल्कि इसको यूनिट, so it becomes p plus qa. ओके सो अगर लेट्स से आपका जो पार्टिकल है, ठीक है, इट्स प्लेस्ड इन एन एक्सटर्नल मैग्नेटिक फील्ड गिवन बाय द वेक्टर पोटेंशियल ए, तो उसका इम्पैक्ट जो है वो, उसके लिए अगर आप हैमिल्टोनियन लिखना चाहते हैं तो जो मोमेंटम ऑपरेटर है उसके अंदर क्यू ए ऐड कर दें। I'm not going into its derivation। आप इलेक्ट्रोडायनामिक्स में अगर ये वो उसका वो मोमेंटम ड्राइव करें तो दैट्स एक्चुअली हाउ द मोमेंटम चेंजेस। और अगर कोई बाहर एक्सटर्नल लेट से कोई पोटेंशियल है, ज़रा कोई और चार्ज है, जैसे हाइड्रोजन एटम में फाई क्या होता है, फाई होता है 1/4 पाई एप्सिलॉन नॉट सम q over r। so this is the potential generated by this plus charge। तो इसको आप इलेक्ट्रॉन ये पार्टिकल के अपने चार्ज से मल्टीप्लाई करें, ई स्क्वायर हो जाएगा। तो दैट्स द पोटेंशियल एनर्जी ऑफ दिस इलेक्ट्रॉन ऑफ द पार्टिकल। सो देन श्रोडिंगर इक्वेशन अगर पहले ये है, तो इट विल बिकम, sorry, the rule is this minus and minus, so this equation will become partial t psi minus q phi, and this will become minus iota h bar del minus qa square over 2m। so ये इक्वेशन बन जाएगी अगर आपका पार्टिकल किसी एक्सटर्नल इलेक्ट्रिक और मैग्नेटिक फील्ड में है। तो या इसको यूं भी लिख लें, iota h bar partial psi by partial t is equal to minus iota h bar del minus qa square 2m प्लस क्यू फी। और अगर बाहर मैग्नेटिक फील्ड नहीं है तो ये जीरो हो जाएगा। सो दिस इज द यूजुअल वे, आपने अक्सर जगहों पे एग्जांपल्स में इस तरह की इक्वेशन देखी हुई है। और ये क्यू फाई जो है ये पोटेंशियल एनर्जी है, ठीक है दिया। ओके सो सिमिलरली जो क्लाइन गोल्डन इक्वेशन है उसमें भी अगर आप जो एनर्जी है उसको बजाय आयोटा एच बार पार्शियल पार्शियल टी से रिप्लेस करें, आयोटा एच बार पार्शियल पार्शियल टी और साथ में ये टर्म भी कर दें, सो देन, और अगर मैग्नेटिक फील्ड बाहर प्रेजेंट है तो ये भी डाल दें। अगर बाहर सिर्फ मैग्नेटिक फील्ड है तो ये टर्म जीरो हो जाएगी, जैसे ये जीरो हो जाएगी, ठीक है। अगर बाहर सिर्फ इलेक्ट्रिक फील्ड है यानी कि कोई और चार्जेस हैं तो फिर ये पार्ट जीरो हो जाएगा। अगर दोनों ही सोर्सेज हैं तो फाई भी है और ए भी है। ओके सो नहीं, so this is just a way to include the external potential। so जो magnetic field है that actually changes the momentum of the particle, so this is that becomes the new momentum। and जो अगर कोई बाहर चार्ज है, कोई बाहर फील्ड है, so it changes the total energy of the particle, so there is another term that is added, ठीक है। okay so let's continue with the Dirac equation। so हमारे पास इक्वेशन बन जाएगी once I substitute everything in, it becomes iota h bar partial by partial t psi 1 psi 2 all the way up to psi n minus iota h bar c alpha 1 del 1 plus alpha 2 del 2 plus alpha 3 del 3 psi 1 psi 2 all the way to psi n plus mc square beta psi 1 psi 2 psi n। ये मैंने इक्वेशन जो है उसको थोड़ा जरा एक्सपेंड करके लिख दिया, और जो P है उसकी जगह पे जो उसकी ऑपरेटर फॉर्म है वो पुट कर दिया, जो मोमेंटम है। ओके या इसको अगर आप By the way, tensor form में लिखना चाहते हैं, so this would be its form. Just to write it in a way that we'll see in most books. So that is actually an equation for each component of psi. Okay? या दूसरे लफ्जों में for each row of left and right side. क्योंकि ये left side भी देखें एक मैट्रिक्स है, एक कॉलम वेक्टर है, right side भी एक कॉलम वेक्टर है. So if we equate, if this column vector is equal to this column vector, each of the corresponding element should be equal. So इसका जो पहला एलिमेंट है वो इसके पहले एलिमेंट के बराबर होना चाहिए. तो इसका पहला एलिमेंट क्या बनेगा? वो बनेगा माइनस आयोटा h bar c j1 to n k1 to 3 alpha ij k partial v partial x k psi j plus j1, बल्कि let me write mc square first, j1 to n beta ij psi j. जी वो मैम कस कर देखा लगती है. So del 1 is partial x1, del 2 is partial x2, and del 3 is partial x3. नहीं, psi 1 तो सब कोऑर्डिनेट का फंक्शन है. psi 1 is function of all coordinates. No, del 1 is acting on everything. क्योंकि ये स्केलर है ना, so the scalar is multiplying the whole vector. इसकी जो पहली रो है वो इसके साथ अप्लाई होगी, इसकी जो पहली रो है वो इसके साथ, इसकी जो पहली रो है इसके साथ. So that's why you see here. So for each psi j, each xk is applied. हाँ देखिए ये है ना डेल. So this is del 1, this is del 2, this is del 3. टेंसर में की जगह जो रिपीटेड इंडेक्स होते हैं, so ये k है, so we can remove this one for this j, so we can remove this one. So अगर आप if you want to use the Einstein notation, then I can remove this thing. So more precisely it's like in component form. ठीक है. देखिए, if you are just working with distances and kinetics, there are no complex numbers in special relativity. But if you are working with, let's say, dynamics or electromagnetic fields for relativistic particle, there are complex numbers. There's no bar on that. देखिए, relativity लेकर आने से complex numbers को क्या होगा? वो तो that's something else that has nothing to do with the relativity. For example, electromagnetics is already fully relativistic, but we use complex numbers all the time. ठीक है. और जिस काम के लिए जो स्पेशल रिलेटिविटी में हम रियल नंबर यूज करते हैं, वो हम इधर भी बगैर रिलेटिविटी के भी रियल नंबर यूज करते हैं. वहां पे मेनली वी आर वर्किंग विद डिस्टेंसेस. ओके, सो डिस्टेंस के लिए तो रियल नंबर पहले भी यूज करते थे, अब भी करते हैं. सो कॉम्प्लेक्स नंबर हैज नथिंग टू डू विद बीइंग इन रिलेटिविटी और नॉट इन रिलेटिविटी. जी ओके, सो this is like the component form of Dirac's equation. All right. Okay, so we still have to find these alphas and beta. So these alpha ij basically are elements of alpha matrix. So when k is 1, so alpha ij 1 are the elements of this alpha matrix, and similarly 2, 3, and beta ij are the members of beta matrix. So how to find these alpha and beta matrices? First of all, these alphas and betas, they're not unique. Okay, but for a given set of conditions that we'll list shortly, they provide the same physical results, even if we get different sets of alpha and betas. So the things that we have at our disposal to find alpha betas, number one is that we see that these alpha k's and betas, they are square matrices. Okay, that's how they will fit in with this notation. The second thing, we know that H, our Hamiltonian operator, has to be Hermitian, which means that our Hamilton, for our eigenenergies to be real, H has to be Hermitian. So whatever alphas and betas we choose, they have to follow this restriction. And by the way, if you apply this, we immediately can find one thing, that each of the alpha k's must be Hermitians and our beta matrix must also be Hermitian. So that's the first condition on our alphas and betas. And number three, which is perhaps the most important condition that gives us these alphas and betas, is that in each individual component, must satisfy Klein-Gordon equation. And the reason we can appreciate that Klein-Gordon equation essentially satisfies that equation, which is also coming out of relativity. The only trouble with that starting ansatz was that our psi didn't have a vector form. So that is an additional restriction. So by using this one and the Hermitian property of these alphas and betas, we can any set of alphas betas that follow these things, they will give same number of the same physical situation solutions. अगर H Hermitian नहीं होगा तो एनर्जी रियल नहीं होगी. H psi is equal to E है ना. So energies, we know that there are real observables. So H has to be Hermitian. क्योंकि जो each component है, जो Klein-Gordon equation, that is also relativistically consistent. Okay, so that's coming out of relativity. So it means each component must satisfy Klein-Gordon equation. Right? Okay, so this means that so continuing number three condition, that each component has to satisfy E square minus P square C square minus M square C4 should be 0 for I1 to all the way to N. So for each psi I must satisfy Klein-Gordon equation. Okay, so let's try to see what conditions alpha and beta should satisfy if they have to satisfy this Klein-Gordon equation for each component. For this, जो वो Dirac's equation है, let me write it again. So Dirac equation was basically this, that E minus C alpha dot P minus beta MC square psi equal to 0. ये वही मैंने ड्रा की थोड़ा जरा और फॉर्म लिख दी. पहले हमने ये e psi एक तरफ लिखा हुआ था और ये बाकी चीजें दूसरी तरफ लिखी थी. So I brought everything on one side. Okay, so let's multiply this whole equation with this operator again. I want to get a form, something like this. So let's operate with this Hamiltonian again. So I'll get E minus C alpha dot P minus beta square MC square. So you can actually in this step, you can also see why Klein-Gordon equation doesn't give us everything. Because it's being obtained from the Dirac equation by operating. So this is essentially, it's going to be a special form for each component of h square psi, not h psi. So since this is just a restricted form, this doesn't give the whole physics. Anyway, so I've operated this since there's a 0 on the right. If I operate with whatever on the left, I still get a 0 on the right side. So let's open it up. So this को open करें. So this E into E is E square. And then let me write the result and then I'll convince you that this is the result that we should get. K1 to 3 alpha K square PK square minus C, the sum over K when K is less than L, and there's a sum over L, alpha K, alpha L plus alpha L, alpha K into PK, PL. Since these are scalar, I don't have to put any dot, etc. These are matrices. So I'm putting a dot to emphasize that this is a matrix product. Minus MC cube K1 to 3 alpha K dot beta plus beta dot alpha K PK minus M square C4 beta dot beta, everything operating and psi is equal to 0. And this can actually very easily be checked क्योंकि ये इसको आप ओपन करें ये सिंपली अल्फा डॉट पी को तो ये तीन कंपोनेंट बनते हैं. दिस इज बेसिकली ये जो पार्ट है इसके अंदर और इसके अंदर. दिस पार्ट essentially becomes sum over K1 to 3 is alpha K PK. ठीक है, ये चीज एग्जैक्टली ये क्योंकि ये डॉट प्रोडक्ट है ना इस वेक्टर ऑपरेटर का इस वेक्टर के साथ, तो अल्फा के पी के पे सम है. यहां पे ये जो इसको आप लिख लें सम ओवर L 1 to 3 alpha L P L and you can get all these terms. Okay, now let's compare. Sorry, ये मैंने बड़ी ब्रैकेट गलत जगह पे डाल दी. Here. Let's compare this equation with this equation. This is the Klein-Gordon equation. So we impose this restriction that each component of psi has to, satisfy Klein-Gordon equation. So now, since this was in E square, so first step we did that our Dirac's equation is, linear in E and P. So we operated with the same Hamiltonian again. Now we have something, in squares. And let's see what are the conditions on alphas, betas, if this has to be equal to this. If this has to be equal to this, it means that a couple of things. First of all, each alpha should square to 1. Each and beta should square to 1. Alpha K, alpha L should anti-commute, which means that alpha L dot alpha K should be 0. And alpha K also has to anti-commute with beta. That means that with plus sign they're equal to 0, anti-commute mean. Because you see that there's this p square term here, right? So p square का coefficient यहाँ पे है minus c square. So this is this p square term, and this is minus c square. If alpha k square is 1 for each k, this would be nothing but p square, right? Now here we have this pkpl term which is absent here. So it means that this should be 0. Similarly here we have a term linear in p. There's no term linear in p here. Ji? ये 3 times नहीं होगा, ये 1 होगा तो this will just be sum over k pk square. So p1 square plus p2 square plus p3 square which is p square. अगर तो ये भी 1 हो जाए तो फिर 3 हो जाएगा, फिर आप सही कह रही हैं. हाँ तो लेकिन ये 1 हो जाएगा तो sum will be just over pk square. हाँ ये p का p1 p2 p3 3 कंपोनेंट. ठीक है. अच्छा ये जो लीनियर टर्म है इसको वैनिश करने के लिए we have to make sure that alpha k and beta they anti-commute, that this sum is 0. So ये हमारे पास सब कंडीशंस आ गई. और ये जो है यहाँ पे बाय द वे और कुछ है. हाँ ये m square c4 है, m square c4. So this beta square has to be 1. जी k is equal to नहीं, k is equal to L, इसमें ये k less than L वाली है. जो k is equal to L वाली टर्म है वो हमने अलग कर ली हुई है. इस सम के अंदर k जो है ना इट्स नॉट इक्वल टू L, k is only less than L. जी L है 1 2 3, तो L जितना भी होगा k will always be less than. अगर k 3 है तो L 3 है तो k होगा 1 2. जी जी. बेसिकली हमने ये किया ना, देखें ये जब इसके साथ मल्टीप्लाई होगा ना तो कितनी टर्म्स होंगी? 3 इसके अंदर है, 3 इसके अंदर है, 9 टर्म हो जाएंगे. यही होगा ना. तो 9 में से 3 मैंने इधर लिख ली है और जो बाकी 6 हैं वो इधर लिख ली है. समझ रहे हैं ना? ये जो पी स्क्वायर ये पी वाली टर्म है वो इन्हीं 2 टर्म से बस आती है. जब ये किसी और से मल्टीप्लाई होते हैं फिर तो लीनियर टर्म आती है ना पी में, वो इधर इकट्ठी की हुई है. तो वो जो k इज इक्वल टू एल वाली टर्म्स है वो इधर है, इसके अंदर है. इसके अंदर k इज इक्वल टू एल कोई नहीं है. Okay. All right. So these are the conditions that our alphas betas have to satisfy. और ये जो number of conditions हैं they're actually less than the number of unknowns. अभी तक जो total condition है हमने उन पे हर्मिशियन वाली condition भी लगाई हुई है अल्फा बीटा पे. वो condition मिला के और ये condition मिला के भी still the number of conditions are less than the total number of unknown alpha and beta. क्योंकि each alpha जो है इसके अंदर n by n unknowns है, इसके अंदर भी n by, तो इसका मतलब है there can be more than one solution that satisfy this condition. But people have checked that it doesn't matter what are those different, all different solutions point to the same physical situation. Okay, and then there's another thing that can be checked numerically, and that is that to satisfy all these conditions, the lowest order has to be n is equal to 4. Other than n is equal to 1, n is equal to 1 will essentially corresponds to Klein-Gordon equation. Okay, because if there's only one component, psi is only 1, then we have seen that this already satisfies Klein-Gordon equation. So this is just Klein-Gordon equation for spin zero particle. After n is equal to 1, the minimum number of n that satisfy all these conditions is equal to 4, actually. N is equal to 4 is minimum n that is required to satisfy these conditions. और इसके लिए for n is equal to 4, for n is equal to 4, the choice of matrices that is most common among people, you know, mostly the people who use that, the choice actually is this: 0, sigma, sigma 0, and beta can be written as identity 0, 0, identity. Where the sigma matrices, actually this is still, these are, you know, vectors. So sigma is defined as this. In other words, you know, I can write this alpha as 0, sigma 1, sigma 1, U3. So this is something we call alpha 1. The next one we can call alpha 2, alpha 3, and so on. So this is essentially the x component, y component, and z component in Cartesian coordinates of this operator alpha. Where sigma 1, sigma 2, sigma 3, they're actually the poly operators. So sigma 1 is poly x operator. It's 0, 1, 0, 1. Sigma 2 is poly y operator. Sigma 3 is poly z operator, 1, 0, 0, minus 1. And beta is already, you know, this is identity, there's a minus sign, sorry, minus here. And this psi vector, which is psi 1, psi 2, psi 3, psi 4, essentially in this one, the first two corresponds to electrons, the second to the antiparticle positron with the negative, the charge opposite of this one. Because to represent spin half particle, we only need a matrix that is a 2 by 1 size. Spin half mean it only have two spin states, either up or down. So for that, any 2 by 1, you know, vector can be used to encode those two states, because we can have, let's say, 1, 0, 1, or the other 1, 0 vector. This can, let's say, encode spin up, and this can encode spin down. So all possible states of a spin half particle can be written as a linear combination of this and this state. And similarly, the all possible states of the antiparticle can also be written as you know, combination of only these two. So that's why, you know, it consistently, starting from there, Dirac was able to show that we can find a way to represent particles, let's say, with non-zero spin. And, you know, another consequence and discovery of that process was that there were other solutions that were, you know, sort of pointing towards the antiparticles of the original particles. So, and that actually later on proved as well when people discovered antiparticles, that Dirac theory was not pointing to something weird, but that was something that also existed. Anyway, so we need to get back to the Dirac equation again and see that if we can solve it for hydrogen atom to see how spin impact the Hamiltonian. Now we are going to take our sigma vector alpha operator like this, beta like this, where alpha has 3 component as actually just like this. And बल्कि अगर इस फॉर्म को आप देखें ना, there's another advantage that we have. We can actually break our 4x4 system into 2x2 system. क्यों? क्योंकि ये देखें जो ये वाली रो है और जो ये रो है, they are sort of being decoupled from each other. So this is a 2x2 matrix, this is a 2x2 matrix, this is whole a 4x4 matrix. ठीक है, लेकिन ये जो 4x4 system है, we can break into two sets of equation, each requiring only 2 component. क्योंकि अभी जो हमने Dirac equation लिखी है, it's like this. Okay, right now we have 8 psi is equal to E psi, but this is a 4x1 vector, this is a 4x1 vector. But we can soon see that we can convert this equation into 2 equation, one for upper 2 elements, psi 1, psi 2, and the other equation for psi 3, psi 4, because both of these equations decouple from each other. Okay. And before that, let's now extend the Dirac equation to a situation when we have external electric and magnetic field. In that case, the equation would become, let's write it here. So now our Dirac equation for a charged particle in external phi and external A. Okay, so we have external electric potential and we have external magnetic potential. In that case, our equation would simply become E minus Q phi minus C alpha dot P minus QA minus beta MC square psi equal to 0. Where now our psi is a 4x1 vector. Okay, so or you can write it in other form, in usual form. Let me keep this E psi on left side and take everything else on the other side. So it will become C alpha dot P and plus beta MC square plus Q phi and minus C alpha minus CQ alpha dot A. Okay, so this is our Hamiltonian now. In the presence of external field, we have a term for electric potential energy and we have a term for magnetic potential energy. So this actually मैं just थोड़ी देर के लिए इस A को रखूंगा, उसके बाद I will make this A 0 as well, because for hydrogen atom we don't need to deal with this complicated term. We'll be just content only with this electric potential term, because in hydrogen atom the electron is present only in a potential created by the nucleus, and that's it. So but for now let's keep this magnetic potential as well, and then later on we'll remove it. So let's specialize to the stationary solutions. Okay, for stationary solution, we can, just as we do in, non-relativistic quantum mechanics, let's say we write our R and T dependent vector wave function as some R dependent vector times exponential minus iota e over h cut t, that type of time dependence. Now, if I substitute it here, so this E is nothing but, so right now it's essentially the operator E that is acting on it. But when this operator is iota h partial t is applied here, we'll get minus iota h e over h bar here. And then this equation will become E chi of R H chi of R. ठीक है, क्योंकि ये जो E ऑपरेटर है, दिस इज पार्शियल टी विद आयोटा एच कट. जब इस पे अप्लाई होगा तो ये माइनस आयोटा ई बाई एच कट बाहर आ जाएगा. So we'll have this E, and then I can cancel out this exponential t on both sides because there's no time dependent operator on this side. So nothing would happen to this term, and this will be cancelled with this on the left. जी सॉरी, काई का क्या? ये वही अगर ये 4/1 वेक्टर, ये भी 4/1 वेक्टर, ठीक है. तो ये चूंकि जनरली तो हमारे पास इक्वेशन, let me actually write it like this. So this is nothing but iota h bar partial by partial t. So this psi is r and t dependent. If we assume psi to be this, then ये जो टाइम डेरिवेटिव है ये काई को तो कुछ नहीं कहेगा, उस पर अप्लाई होगा. तो बाहर आ जाएगा e ओवर h बार माइनस आयोटा, तो और पार्शियल पार्शियल t दोनों तरफ से कैंसिल कर दें, तो यू विल बी लेफ्ट विद दैट इक्वेशन. जो बेसिकली इट्स द करस्पॉन्डिंग टाइम इंडिपेंडेंट Dirac इक्वेशन, जिस तरह टाइम इंडिपेंडेंट श्रोडिंगर इक्वेशन है. सो दैट्स द टाइम इंडिपेंडेंट Dirac इक्वेशन. ये रेडियल पार्ट नहीं करना चाहिए, स्पेशल पार्ट करना चाहिए. रेडियल तो सिर्फ वो एक आर होता है ना, तो स्पेशल में आर थीटा फाई या एक्स वाई जी तीनों होते हैं. समझ रहे हैं इस बात? ओके, ऑलराइट. सो वी नो हैव an equation for stationary solutions. And let's write this chi, which is a 4/1 vector, as composed of two vectors, psi 2/1 and eta 2/1, and then put it in our equation, and we will get E psi eta minus iota h bar c, and this alpha was 0 sigma 0 dot del minus CQ 0 sigma 0 dot A plus Q phi plus identity 0 minus identity MC square into psi eta. अब अगर हम पहली रो को देखें तो पहली रो बनेगी E psi और माइनस आयोटा h कट c 0 into psi plus sigma into eta, sigma dot del eta. फिर इससे जो पहली रो बनेगी माइनस सी क्यू 0 into psi sigma dot a into eta, sigma dot a into eta plus q phi into psi, और ये फिर प्लस आई प्लस एम सी स्क्वायर आई इंटू साई। ये पहली रो से इक्वेशन बन जाएगी। दूसरी रो से बनेगी ई ईटा माइनस आयोटा एच बार सी सिग्मा डॉट डेल, और ये सिग्मा इंटू साई होगा, फिर माइनस सी क्यू सिग्मा इंटू साई 0 इंटू ईटा प्लस क्यू फाई, तो ये नीचे वाली से ईटा हो जाएगा, प्लस एम सी स्क्वायर बल्कि माइनस एम सी स्क्वायर ईटा। अब ये हमारे पास दो इक्वेशंस आ गई हैं। अच्छा, मैं पहले कह रहा था अनकपल, अनफॉर्चुनेटली अनकपल नहीं हुई, बल्कि दे आर स्टिल कपल्ड। अलबत्ता वी नाउ हैव टू सिंपलर इक्वेशंस। So these two equations where each of the equation now involve only two spinners. ये जो है ना, इसको हम कहते हैं टू स्पिनर, ये भी टू स्पिनर है, और ये जो पूरा है वेक्टर इसको फोर स्पिनर कहते हैं, क्योंकि उसके फोर कंपोनेंट थे, इसके दो कंपोनेंट, इसके भी दो कंपोनेंट। यू सी देयर मैट्रिक्स मल्टीप्लिकेशन, जैसे देखें ये मैट्रिक्स से मल्टीप्लाई होगा तो ऐसे ही होता है ना, रो इनटू कॉलम। सो आई इंटू साई प्लस 0 इंटू ईटा, ये पहला एलिमेंट बन जाएगा। सो ये साई लिखा हुआ है, ये एम सी स्क्वायर तो स्केलर मल्टीप्लाई हो रहा है, ये स्केलर है तो दिस जस्ट मल्टीप्लाइज टू दिस वन एंड वी गेट दिस वन। ये पहली रो से आएगा, दूसरी रो से आएगा, यानी पहली इसकी दूसरी। इस तरह से ये टर्म है, ये है सी क्यू, अब 0 इंटू साई, ये डॉट ए के साथ भी, और सिग्मा इंटू ईटा। सो ये तो 0 है, तो ये ईटा जो है ना, ये इसके साथ आ गया। और सॉरी, ये जैसे ये मैट्रिक्स है ना, तो इसका सिंपलेस्ट वर्जन ये है, अगर ए बी सी डी हो, x1 x2, तो इसकी पहली रो क्या होगी, ए एक्स वन प्लस बी एक्स, ये होता है ना, ये इसके साथ, ये इसके साथ। हाँ हाँ, इसकी, हाँ तो ये तो कांस्टेंट स्केलर है ना, तो ये इसके साथ मल्टीप्लाई इसके साथ भी होगा। ठीक है, तो लेफ्ट साइड पे जो वेक्टर है उसमें ई साई और ई ईटा दोनों है। ठीक है, आप अगर थोड़ा ज्यादा कंफ्यूजिंग फील करें तो आप इसको यूं समझ लें, लेट मी पुट एन इक्वल हियर, दिस इज अ वेक्टर एंड दिस इज अ वेक्टर एज वेल। तो इसके बाद ये जो पहली रो है उसको पहली रो के बराबर कर लें, दूसरी रो को दूसरी रो के बराबर कर लें। हाँ तो ठीक है, तो आप, लेट मी टेक दिस एग्जांपल, आप थोड़ा सा कंफ्यूज हो रही है क्योंकि नॉर्मली हम सिर्फ स्केलर नंबर की लेट से अगर है कोई मैट्रिक्स ए 0 0 बी, यहाँ पे कोई ये लेट से x1 x2 है, y1 y2, तो अगर आप इस a को यूं समझे a1 a2 a3 a4 और 0, तो होना चाहिए ना a1 x1 प्लस a2 x2। लेकिन अगर मैं इसको a ही लिख दूं और इसको मैं सिर्फ x कह दूं, तो यहाँ पे लिख दूं ax, तो अल्टीमेटली वो बनेगा तो वही, फिर ये ax का मतलब वही है a1 इंटू x1 a2 इंटू x2, तो जरा वो कंप्रेस नोटेशन है। ठीक है, सो बेसिकली ये जो दो इक्वेशन है ना, इन दो को सॉल्व करके हम किसी भी जो कोई भी चार्ज पार्टिकल जो एक्सटर्नल फील्ड फाई और ए के अंदर है, उसके लिए वी कैन सॉल्व इट, we can we can get equations to find solution for a particular situation. And let's actually leave it for the next lecture, उसमें हम इसको हाइड्रोजन एटम के लिए स्पेशलाइज करेंगे by taking a0 and then finding what the equation Hamiltonian should be. बेसिकली इनकी जो प्रॉपर्टी, जो पार्टिकल और एंटी पार्टिकल दोनों मैटर हो सकते हैं, हम मैटर और एंटी मैटर कह लें, but that designation is arbitrary कि which one is called matter and which one is antimatter. बल्कि टोटली इट्स नॉट टोटली आर्बिट्रेरी. जो आजकल एग्जिस्ट करता है, जो पार्टिकल्स उनको हम मैटर कहते हैं, which have shorter lifetime, for example positron, we call them antimatter. But in someone else's universe, we might be living an extremely short life and they might be living a very long life, and we then would be antimatter and they would be matter. Okay, so पता नहीं आप लोगों को कितनी समझ आई है, but I think it's not that difficult. The only thing that is perhaps more than Schrodinger equation कि आपको वेक्टर साइज से आप डील करना पड़ता है बजाय एक स्केलर साइज के. So math gets difficult. That's the only part. जी आसिफ.
सर आपने कहा ना कि n is equal to 4 के लिए, तो ये n is equal to 4 उधर जो समेशंस है उधर n की वैल्यू 4 तक रन करेगी. जो
साई है, जो कैपिटल साई है, उस पे
आपने सॉल्यूशन फाइंड किया कि n, जो पिछली बोर्ड पे आपने इक्वेशन डिराइव किया ना, तो आपने कहा कि n is equal to 4 के लिए ये n is equal to 1 क्लाइन गॉर्डन देता है और n is equal to 4 के लिए ये डिराक इक्वेशन देता है.
नहीं,
तो
डिराक इक्वेशन
इज
सो डिराक इक्वेशन है ना, वो n ग्रेटर देन 1 के लिए इट्स डिफरेंट फ्रॉम क्लाइन गॉर्डन इक्वेशन. प्लस जो n is equal to 4 है, दैट इज द मिनिमम रिक्वायर्ड फॉर डिराक इक्वेशन. n greater than 4 is also possible. For example, अगर आपके पास 3/2 spin के पार्टिकल हैं, तो I think you will need a psi vector that has 8 elements.
ठीक है सर. तो ये n is equal to 4 कहाँ से आ गया? मतलब
ये जब जो ये कंडीशन है ना अल्फा और बीटा पे, तो वो फुलफिल मिनिमम n is equal to 4 के लिए होती है.
ठीक है. तो वहां पर तो कोई इंडेक्स है नहीं है, n वहां पर कोई नंबर तो नहीं है पहले से n?
हाँ, उसमें नहीं है, लेकिन if you have n less than 3, you cannot fulfill the requirements of alpha beta being Hermitian and they squaring to 1 and they satisfying the anti-commutator relations.
ठीक है. जो कंडीशंस हमने उधर कोएफिशिएंट्स के ऊपर लगाए हुए हैं, तो वो n is equal to 4 के लिए सारी ओबे होती है.
n is equal to कम से कम n 4 होना चाहिए,
ऊपर जितना भी हो. n की वैल्यू मींस 5 6 7.
नहीं, n1 भी पॉसिबल है, आप ये नहीं फॉलो, n1 के लिए भी हो जाएगा, लेकिन n1 के बाद n4 है.
ठीक ठीक
ठीक है.
ठीक.
क्योंकि जो n1 मीन साइज स्केलर, तो उसके लिए तो सेटिस्फाई करनी चाहिए वो, तो इट शुड रिड्यूस टू श्रोडिंगर इक्वेशन फॉर नॉन रिलेटिविस्टिक केस एंड फॉर रिलेटिविस्टिक इट शुड रिड्यूस टू क्लाइन गॉर्डन.
ठीक.
थैंक यू. ओके जी, so let's meet on Wednesday to conclude it. Thank you.